Welcome you all for the structure analysis course. This is CDT3 continuation, shear force and bending moment diagrams, and shear force diagrams and bending moment diagrams, and elastic curve for the given continuous beam. So in this session, we want to draw the bending moment diagram as well as shear force diagrams for the given continuous beam. So in the previous lecture, we discussed about the analysis of continuous beam. That means we are calculated final movements. So once again, we will see step-by-step procedure. The step one, we are calculating the fixed moments for the two spans. So for the span AB as well as for the span BC, we have calculated the fixed moments. So here we have fixed moments. MFAB is equal for span A, concentrated point load is acting. So that the calculation of fixed moments can be calculated from this formula. If point load is acting at the center, then fixed moment is WL by 8, or there is P, then it will be PL by 8. This is in anti-clockwise direction, so that's negative. And here we have MFBA, that is positive, that is PL by 8, because it is the shifting moment is acting in the clockwise direction. So we substitute these values, you are going to get minus 20 kN meter, as well as MFAB is minus 20 kN meter, and MFBA is plus 20 kN meter. So coming to span BC, so that is span is subjected to uniform distributor load. So if uniform distributor load is subjected, beam is subjected to uniform distributor load, the fixed moments, that is MFAB, will be equal to minus WL square by 8. This is acting in the anti-clockwise direction. MFBA, which is acting clockwise direction. So this is positive. So positive WL square by 12. This will be MFAB will be minus WL square by 12. So from this formulas, if you want to calculate, you can calculate this one. For the second span, MFBC is equal to minus 60 kN and MFCB is equal to plus 60 kN meter we are getting. So after calculation of fixed moments, we need to develop slope reflection equation for two spans. So just substitute theta value and delta values, these two equations. We are going to develop the four equations. This is equation number 1, MAB final moments. So final moments equations we are going to develop. This is equation number 3 and this is equation number 4. The only thing what we need to do in this equation, MAB, slope reflection equation, final moment MAB will be equal to MFAB plus 2A by L, 2 theta A plus theta B minus 3 delta by L. In this equation, substitute for the in the given figure, two extrements are fixed and it is joint. It is a roller joint, roller support. This is a roller support. So at roller support, theta B is equal to theta B. Let us say this A and this B and it C. Theta at B will be theta B. Theta at A will be equal to 0. Theta at C equal to 0, and the delta for all the supports will be equal to 0. So by using these conditions, substitute these conditions in the equation for the span AB as well as for span BC. For AB span and BC span, if you substitute it, we're going to develop these equations. So these are called slope reflection equations. So we're going to develop four slope reflection equations for the two spans. Okay. So after developing the slope reflection equations, so we need to write the joint equilibrium equation. So for the joint equilibrium equation, we consider this is our given beam. For this beam, we observe support A and support D are the fixed support. That means moment at A as well as moment at C will not be equal to 0. Is not equal to 0. Some fixed moment will be there. At the B is also some negative moment is there, but the thing is summation of moments at B will be equal to 0 because this is a intermediate support and it is a roller. So from the joint equilibrium equation, summation of moments at B equal to 0. That means at B we have two moments, MBA, MBC. So we can write like this, MBA plus MBC equal to 0. So this is a joint equilibrium equation. So from the joint equilibrium equations, so we have calculated MBA and we are already calculated MBA and we are already calculated MBC. So this is MBA and MBC. You add 2 and 3 and equate it to 0. equated to 0, you're going to get EI theta B value 17.143 we are getting. 17.143 we are getting. So now substitute EI theta B value in this 1, 2, 3, 4 equations. 1, 2, 3, 4 equations. We're going to get the final moments. So final moments we are getting MAB is equal to minus 11.428, MBA is equal to 37.143, MBC is equal to minus 37.143, MCB is equal to 71.429. So now, so this up to this part we are discussed in our previous CDT, that is continuation of the CDT3 we are discussed. Now continuation of the CDT3. So this is the calculation of shear force, drawing of shear force diagrams and bending moment diagrams. Okay, so for that, for developing shear force diagrams and bending moment diagrams, so first of all, what we need to do is we need to draw the free body diagram of the free body diagram. We need to draw, right? So I want to draw the actual structure here. This is a roller support and it is fixed one. This is a roller one. This is support A and it is B and it is C. Okay. AB span length is 4 meters and it is subjected to 40 kilonewton load, and BC span is subjected to uniform distributed load. Its intensity is 20 kilonewton per meter and its length is 6 meters. This is 6 meters. This is 4 meters. Okay, so this is the given figure. So now what we calculated, we have calculated MAB. MAB is equal to some 11.424. MBA is equal to, this is minus and this will be 37.143. We are also calculated MBC is equal to 37.143. This is negative anti-clockwise. MCB is equal to 71.424. So now from this given data, we are calculating these values. So we have to draw the free body diagram of these two spans. If you draw the free body diagrams individually for the AB span and BC span, we can observe here. At A, we have fixed moment, that is MAB, so 11.48. How we are getting this value? So these values we are calculated from here. So MAB is equal to minus 11.428. Okay. MBA value is 37.143. This is acting in clockwise direction. So now MBC is equal to 37.143, which is acting anti-clockwise direction, and MCB, which is acting clockwise direction, 71.424. Okay. Yeah. So now for the drawing of shear force diagram, we have to calculate the reactions RA, RB1, RA, RB1, RB2, and RC. So these values we need to calculate. For the calculation of RA, these values. So first of all, what I want to do is I want to take for the first span, for the AB span, I want to take moment about B, summation of moments at B equal to 0. So now if you do the summation of moments at B equal to 0, then I'm writing here RB1 effect will be 0. The force RB1 effect will be 0 because the line of action of force is passing through point B. Line of action of force is passing through point B. So now if you take this, if you consider all these forces, write the end moment, and I'm writing here bending moment for I want to take the bending moment at B equal to 0 for the first span. Summation of moments at B equal to 0 for the first span. Then you're going to get, so we have, I'm considering anti-clockwise is negative and clockwise is positive for the calculation of RA value for taking moment about B. So now here we have RA. So RA So if we are taking moment about A, moment about B, RA effect with respect to B, which is acting in clockwise direction. So clockwise will be considered to be positive RA into this span. So span is 4 meters. As we know, this span is 4 meters. So RA into 4, that which is producing clockwise effect. And another force is there. This is 40 kilonewton, which is producing anti-clockwise effect with respect to B. So that is 40 into 2. 40 into 2. And also two moments is there. 11.424 one moment is there, that is acting. 11.424 is acting, which is anti-clockwise direction, minus 11.424 which is acting anti-clockwise, that is negative. And 37.143 which is acting clockwise direction, that is positive. 37.143, so equal to 0. So if you solve for RB, you are going to get RB value, sorry, if you solve for RA value, you are going to get 13.571 kilonewton. So 13.571 kilonewton we are getting. So after calculation of this RA from vertical equilibrium equations, summation of sigma Fy is equal to 0 from sigma Fy is equal to 0 for span AB. That means RA plus RB1 equal to 40 kilonewtons. From the vertical equilibrium, sigma Fy is equal to 0. So RA value we are getting. So substitute RA value in this equation, you are going to get RB1 will be equal to RB1. You are going to get RB1, you are going to get 26.429 kilograms. 26.429 kilograms. So similarly, you apply the moment at C equal to 0, so moment at B equal to 0 for the second span, you are going to get RB2 will be equal to, you are going to get RB2 is equal to 54.286. So take moment about C equal to 0, moment about C equal to 0 for the second span, moment at C equal to 0 for the second span, you are going to get RB2 is equal to 54.286. And similarly from the sigma Fy is equal to 0, if you apply, that is upward force will be equal to downward force, that is 20 into 6 will be equal to RB2 plus RC. If you substitute in this equation, you are going to get RC value. So RC, reaction at C 65.714 kilonewton we are getting. So after getting these values, so we need to move for the drawing of shear force diagram. So we need to go for the shear force diagram. So we know RA is equal to 13.571, RB1 value 26.429, and RB2 54.286, RC is equal to 65.714. So these are the values. So first you have to understand the concept of how to draw the shear force diagram. So shear force diagram can be drawn from this condition. So this is the condition you need to remember. The condition is right side for drawing of shear force diagrams, right side upward force considered to be negative. Right side upward force considered to be negative. Right. Okay, I'm coming from left to right. So what is the value at C? Reaction at C is, at C we have reaction RC is there. I want to draw the shear force diagram from right to left. If I want to draw the shear force diagram from right to left. If you go from right to left, at C, from C to A I am moving. At C we have a reaction, that is reaction at C. The intensity of that is the magnitude of RC is 65.714. So this is right side. This is acting of upward force. Right side upward force will be negative. So you need to represent the negative side. So I am represented here 65.714. So this force is acting downward direction. Applied uniform distributed load is acting downward direction. So downward effect will be positive. Right side downward force will be considered to be positive. Okay, right side downward force will be considered to be positive. The variation of the shear force diagram due to uniform distributed load is a linear variation. Linear variation, that is the linear variation. Somewhere it will be zero. Somewhere it will be zero. Just drag up to here. Somewhere it is here zero, and this will be positive after some distance. Okay, so at b we have another right side upward force. This will be from, we are coming from right to left now, so this will be considered to right side upward force. So that is rb2 will be there. rb2 value 54.286. You locate 54.286 point approximately, and okay, another force is there. That is you forward up to here, pass that is after that you're going to get rb1, that is 26.282.429. So similarly, if you draw for this beam, you're going to get the variation of shear force diagram. Okay, right. At rb1 26.429, this is acting negative value. This is 54.286. So this is coming from negative side, and this is up to here. There is a no change. At this point, 40 kilonewton load is acting. So 40 kilonewton load acting load suddenly. So right side downward force. Right side downward force will be positive. Right side downward force will be positive. So we need to move to the positive side. So 26.429 minus 40. 40 minus 26.429, you're going to get 13.571. 13.571. So you need to represent here. And up to before a there is no change. Before a there is no change. At a, the reaction at a is 13.571. So it will approach us to 0. So you need to remember these two things. Right side upward force to be negative, right side downward force will be positive. So right side upward force, negative side you need to represent. Okay, right side downward force positive. That means this negative value gradually decreasing to 0. From 0 to it is increased to positive value. Again, right side downward force is acting, that is negative. So 54.286 is there. Resultant here we have 54.286 there. RB2 is 54.286. It will become, that means negative. We need to deduct from 54.286 minus 54.286. We are getting shear force at this point is 0. Again, just if we move forward, we'll go and get RB1. RB1 intensity 26.429, which is acting upward direction. So right side upward force will be negative. We need to present negative side. After that, up to before 40 kilonewton, there is no change. At 40 kilonewton load, suddenly downward force. So right side downward force will be positive. So positive side we need to move. So that means 40 minus 26.429, you will go and get 13.571. So before A, after 40 kilonewton and before A, the same load will be continued, same shear force will be continued, but at A, because of reaction at A, so reaction at A is 13.571. So this 13.571 minus 13.571, both are 0. That means shear force at A will be 0, shear force at C will be 0, shear force at A will be 0. So now we can draw the shear force diagram from this. You just join all these points, you're going to get the shear force variation. You join all these points, you're going to get the shear force variation. So this is the shear force variation. So this is a negative shear, and this will be positive shear. This is a negative shear, and this is positive shear. So this is the shear force variation. Now we'll move to the bending moment calculations. Okay. So for that bending moment, for that what we have to do is, first you have to represent MAB. So MA is E is equal to 11.428. MBA is equal to, I'll write here. MAB is equal to 11.428. This is a negative sign, anti-clockwise. MBA is equal to positive 37.143. MBC minus 37.143, MCB 71.429 kilometer meter. So you have to represent all these points first. So negative bending moment diagram on first draw చేద్దామండి. So first MAB is equal to 11.48 draw చేశాను, రిప్రజెంట్ చేశాను. తర్వాత so MAB, MBC, MBA, MBC are same, that is 37.143 represent చేశాను negative side. And MCB కూడా 71.429 ఇది represent చేశాను. This is arcing bending moment. This is arcing bending moment points represent చేశాను. So now what you have to do is you just join all these points. Join all these points. So this is the variation of negative bending moment diagram. This is the variation of negative bending moment diagram. Now we need to draw the positive bending moment diagram. We need to draw the positive bending moment diagram. So positive bending moment diagram will coming from, it is from applied load. So this point load is there. So point load ki maximum bending moment formula is WL by 4. Okay, WL by 4. So calculate WL by 4. W value 40, L value 4 divided by 4. L value 4 divided by 4, you will go to get 40 kilonewtons. So the variation of bending moment diagram due to point load is a linear variation. So this is a linear variation. Here maximum వస్తుందండి, ఇక్కడ 0, ఇక్కడ maximum, and again here it is 0. So like that you need to represent for the first span. Similarly for the second span, at B bending moment is 0, at C bending moment is 0. This is I am saying about a fast sagging bending moment. Sagging bending moment I am saying. At the center it will be maximum. Center of the second span it will be maximum, that is WL square by 8. This all WL square by 8, you are going to get 90 kilonewton meter. So the variation is parabolic variation. You represent the parabolic variation. Okay, there is a parabolic variation. So if you observe, so this is the variations. So positive bending moment and negative bending moment diagrams. Now we need to locate net values, net positive and net negative. So that is the actual bending moment. So actual is nothing but net value. So this is will be the negative and this will be positive. This is negative and this will be positive. This will be called net negative bending moment diagram. That will be called net negative bending moment diagram. So this is net negative and this is net positive. This is net negative and net positive and net negative. Now I want to show you the same thing. I want to show you the same thing in start pro. So I am consider this is the given diagram. This is fixed and this is also fixed. First span is 4 meters, second span is 6 meters. First span is subjected to 40 kilonewton load and the second span is subjected to 20 kilonewton per meter. Now we will see the variation of bending moment diagram. The variation of bending moment. So this is the variation of bending moment. At A, here we are getting the value. Here we are getting the value 8.169. At B, we are getting 43.939. At C, we are getting 67.989. So these values are different from our calculated value. Why? Because this approach is different. Here, the start pro will approach finite element analysis. So matrix approach we are doing in slope distribution method of analysis. So that's why these values are different, but the variation is same. You can see the variation is same. Okay, the net values we are representing the net bending moment diagram. We are drawing only net bending moment diagram. So here net value is 8.169. Here 43.9. So you can see the other values also. Okay, here we are getting the value 13.946. Okay, here we are getting 43.9. 939. Here we are getting 34.036. Here we are getting 67.989. So these are the net values, net bending moment diagram values. Now I want to show you the shear force variation also. The shear force variation. So this is the shear force variation. At A we have reaction at A is 11.058 kilonewton. So this is different. Some less values we are getting here in start pro. Okay. At B minus 28.942 and 55.992 kilonewton. Okay. At C 64.008 kilonewton. So this is the variation of bending moment. We are modeled same thing in start pro and we are observing. Okay. So this is the how to draw the shear force and bending moment diagrams. So thank you one and all.